to AdaptNow, the ABB podcast series on adaptive execution. Hi, everyone. This is Dan Overly. Welcome to another edition of AdaptNow, our technical podcast series on topics related to ABB Adaptive Execution and some of the technologies behind ABB Adaptive. Today we have Steve Royston with us. Hi, Steve.
Hi, Dan. Hi, everybody.
Hi. Steve's coming to us from the UK with ABB, and he's been with ABB a number of years. Maybe you could just start by telling everyone your background, Steve.
Yeah, I'm an automation engineer. I actually joined ASEA, which is the A part of ABB, over 36 years ago. So I've had a lot of experience working with ABB, mainly as an automation engineer. Graduated with a BSc in electronics and electrical engineering, and my whole career with ABB, I guess the first 10 years spent as a systems engineer, engineering automation systems and installing them and commissioning them in different industry areas, including predominantly oil and gas, and then 10 years in bid and proposals, doing sort of multinational bid and proposal work for the sales organization. And then the last 10 years I've been mainly working in technology management, again, mainly in the area of automation.
Mm-hmm. Great. Well, for the topic today of simulation and its role during project execution, in the whole phases of execution of a project, you eminently qualified to talk about. So I just want to begin with what is the difference between simulation and emulation? I hear those two words interchanged these days.
That's a really, really good question. And I guess from my perspective, it's probably more about kind of the two words are used very often to try and describe the same thing, but what we try to do is to use the two words to describe two different things. And in my opinion, that both words describe the fact that we're trying to mimic something. When we try to simulate something, we're trying to mimic something, and when we emulate something, we also try to mimic something. But to me, the principal difference between the two are that when it comes to simulation, particularly when we talk about process simulation, where we're building a model to simulate a process, where we might be using physics to build that model, we get somewhat an approximation. We don't get the exact replica of the process. It's very difficult to get to that level of fidelity and detail and realism to completely 100% simulate a process, whereas emulation is really a 100% simulation of something. It's for example, if we're trying to emulate, if we take a PLC, for example, which is a piece of hardware that we have made to be very ruggedized and sit out in the field, and we can program this programmable logic controller with some automation logic in there to perform a task. And what we want to do nowadays is to make a software emulation of that PLC controller so that we can build its control logic in the cloud. But that emulation needs to be a 100% replication of how the hardware behaves, the PLC hardware behaves. So for me, emulation is really a 100% faithful copy in software of the hardware that we're trying to emulate, and simulation is as best an approximation as we can get. So that's the best way I can describe it.
Well, that's helpful. Maybe as in the course of this discussion, you could further elaborate on the use of those two words. And I mean, how does that fit into the topic of a digital twin in that expression?
Well, again, digital twin has many different meanings, and I think very many different connotations. And there isn't really an industry standard that defines what a digital twin is. And we use digital twinning to describe a lot of different scenarios. For example, in our System 800XA automation platform, we have there an object-based orientated data structure, and we build objects within our System 800XA that kind of mimic the real physical plant assets like pumps and motors, etc. So you could argue that the object that we model in software within the 800XA system is a digital twin, a type of digital twin. But also a digital twin can mean that you're building a physical model of a particular asset, and that physical model can be used then to allow software applications to use that model to optimize operations associated with that particular asset, or optimize production associated with that asset. So the digital twin is very much centered around these simulation models that allow you to use these models to then optimize your operations around that particular asset. But again, it's a very open and subjective term, digital twin.
Yeah. Yeah, I hear it used a lot. I guess moving into the role this topic plays in ABB Adaptive Execution, let's start with the design phase. Where does the simulator play a role there?
Well, we have a product which we call a lifecycle simulator, and this simulator is really, to go back to the term emulation, it's emulating the real physical automation system that you might install in a production plant. And our lifecycle simulator is really an emulation of that of the physical hardware for the automation system that would be installed on a production system. And when we connect that to a simulation of the process, using a high fidelity process model, for example, then this becomes what we call like a virtualized engineering environment, so that we can build our application software and test it in this virtualized environment prior to downloading that application software onto the real physical hardware for the production system. So I think from that perspective, the lifecycle simulator is really like a digital twin of the automation system solution and the process that it's controlling in the real production environment.
Just to go back to those two words, emulation seems to be a reflection of the hardware in the design, and simulation is a reflection more of the software that runs the process.
Yes, that is exactly what it is. And I bring in another term, like a lot of people use the word virtualization and talk about virtual PLCs and things. So in other words, virtual PLCs are really an emulation of the real physical PLC. So just to bring in another term there, that virtualization is another term that's used to describe possibly two different things. And virtualization is also used in IT technology to describe kind of consolidation of server hardware. So we would prefer to reserve the term virtualization to describe that technology, and then use emulation to describe our kind of simulating a PLC with a software application.
Okay, got it. What about, you mentioned 800XA, the process simulation. What about electrical? Does that get simulated as well?
Yeah, I mean, we have recently developed a product called Process Power Simulator, and where I think everybody is possibly used to hearing about the fact that you can procure process models that will simulate a process in terms of the levels and pressures and temperatures and the thermodynamics of a typical industrial production process. But we have developed another simulation, which is process power simulation, which is simulating the electrical characteristics of a power distribution network in terms of voltage, frequency, and current. And we've developed this specifically because ABB, we're in the business of supplying fully integrated process and safety automation together with power automation. So we want to really produce a complete digital twin. And in order to do that, we need to complement the process model or the process simulation with an electrical simulation. And this is what we refer to as our process power simulator. So when we combine process power simulator together with our process model, and we connect these to our training simulator, then we produce a very comprehensive digital twin that we can then use to design and test and train people on our integrated process safety and power automation system solutions.
So it's a digital twin of the plant design. And then does the electrical simulation give you an indication of the loading on the electrical system as part of the design?
Yeah, exactly. So it can react to the process simulation and provide simulation of the power and the voltage and current that you might expect from a motor when you're when you're using that motor to run a pump, for example, on the process. So the process flows that the pump will create in the pipe work in the process pipe work. Then the electrical simulator will correspondingly provide you a simulation of the voltages and the current and the frequency that will be created inside the motor that's driving that pump, that's driving the process fluids. So it's really giving you a comprehensive digital twin for the overall system.
So do you use this digital twin, basically when you have this set up, do you use this to select sizing and proper process and electrical equipment for the plant?
Yeah, this is primarily why we don't really refer to our training simulator as a training simulator as such. We refer to it as a lifecycle simulator because when we enhance this product with an electrical simulation together with process simulation, we can use it throughout the entire project lifecycle. So we can use this electrical simulation very early on in the design phase for purposes exactly as you describe, that we can use it to potentially spot undersizing and oversizing of electrical motors that are driving pumps. And this has big benefits in terms of, as you can imagine, that if we're oversizing pumps and we can use the electrical simulator to spot an opportunity to put in a smaller electric motor on the pump and still gain the same kind of process parameters that we need, then we're saving capital expenditure on the product. So this means that we can use this simulator much earlier in the project life cycle and gain extra benefit from the investment.
Yeah. So what about during then the execution or the staging part of the project? Does simulator play a role there?
Very much so. I mean, you can the advantage of being able to use process and electrical simulation during the kind of design and engineering phase of an automation system solution is that you can test the application's software in a much more realistic environment, and so that you can get a lot more value out of the testing. And in fact, as you increase the fidelity of the models throughout the project lifecycle, in other words, as the models become more realistic, then the testing that you perform using those models almost comes to the point where you can call it virtual commissioning. And you can really start to reduce significantly the amount of effort that you will use in terms of on-site commissioning, because you will reveal a lot of errors much earlier in the project life cycle in a virtual environment where the costs to rectify those errors that you might find are far, far cheaper than finding them with people commissioning on site. So we've proven this on a number of projects, that using a high fidelity simulation for the process and electrical worlds when you're testing your application software can save you significant effort when it comes to working on site. And as you can imagine, the cost benefits are tremendous, but when you save hours on site commissioning. So this really does allow you to what we would call virtual commission the application software.
Yeah, I've always been curious. Is there like a certification that has to take place for clients to feel comfortable that the simulator is truly, reflecting the real world, such that they feel confident in that virtual test?
I'm not so sure that there's any kind of certification involved in it, but these kind of building these physical models is kind of based on physics and the knowledge and experience of the people building the models, and so I don't think that there's any kind of certification as such to kind of define, to sort of certify their fidelity. Mm-hmm. But they certainly will give you a lot of benefit in terms of being able to prove your application software is working correctly, particularly when you want to develop applications whereby you might want to start up and shut down the process with single push button starts and using a lot of sequential logic to start up your pumps and open valves and wait for flows to increase and things. You can do a lot with these simulations to get those startup and shutdown sequences extremely accurate, and save much time on site in commissioning them, and being able to start up and shut down these plants quickly and efficiently with more automated logic has huge benefits in terms of operational and total cost of ownership.
I would think too that the typical deluge of alarms that you get during startup probably get reduced when you've got it wrung out pretty well via the simulator.
Yeah, and I mean that's another very interesting topic, because we've been asked by many of the large national oil companies that can we use simulation in order to test their alarm management strategies, so that we can actually use simulation to test and verify that their alarm management strategy is giving them the KPIs that they require in order to meet industry standards like EMUA 191 in terms of alarm frequency and standing alarms and stuff. So that's a very interesting topic that we can explore now that we have these simulations available to us during the engineering phase. Mm-hmm. That's probably moving a little bit into the future, but it's something to bear in mind for sure.
Okay. So what about after startup? Does the simulator get used still during operation?
Well, I mean, the primary reason for developing our training simulator was, as its name suggests, is that with the training simulator you can train your operators to be able to operate the plant in an offline scenario prior to when they come on to actually control the real live plant. And the primary reason for developing this product was really to allow end users to train their operators in a classroom environment to be able to operate their plant using a simulation model that would give them a very realistic feedback in terms of the plant dynamics and the time taken for levels to rise and pressures to build and flows to build up, and give them real scenarios where they can look at what might need to be done in terms of mitigating high pressure alarms and things like this. But we've also realized that, as I suggested earlier, that if we can use the models early in the project lifecycle in the design phase, then we can use them much earlier. But also post-operation, after you've trained your operators, these simulators still have a very high value in terms of allowing our end users to be able to design and build and test modifications to the automation strategy, and being able to test those modifications and the effects that they might have on the process in an offline environment prior to actually downloading those modifications into the real production plant. And there have been many instances where we have made modifications to automation system solutions on a running plant and inadvertently tripped it or inadvertently affected the quality of the production temporarily while we've been making those changes. If you have a lifecycle simulator with a high fidelity process and electrical model, then you can make these modifications and test them offline and virtually commission them prior to downloading onto the real production system, so that you can be sure that when you introduce these changes, you're not going to adversely affect production or cause any trips or change the quality of the product, for example. So they have huge benefits in terms of post-operational.
Well, this just sounds, I mean, this sounds like a very key element to the whole ABB adaptive execution. I mean, you've said change and modification, and I mean, it's all about adapting to new design requirements after startup. And so to me, it's very clear a key element to the methodology of ABB Adaptive.
Yeah, and I mean, I would say that process and power simulation and the use of our lifecycle simulator platform are kind of key and central to the whole ABB Adaptive Execution theme, and particularly because they bring so much value and benefit to every stage of the project life cycle, not just from the point of view of training operators, but also during the early design phases, all the way through the engineering, and then huge benefits when it comes to lowering your overall operational costs and the total cost of ownership. So yeah, I think for me, simulation is key, is a real key component of ABB Adaptive. And like you say, being able to adapt to using simulation to be able to implement changes and adapt to modifications in a very quick and risk-free manner is central to the whole ABB Adaptive Execution philosophy.
Well, that's been really interesting for me. I mean, simulation in my history, my experience was sometimes considered nice to have. Now it just sounds like a must-have to really deal with the future and living in a kind of a constantly changing world. So
definitely. I mean, I think simulation is essential for the future. I mean, if you think of the ultimate goal of having autonomous plant operation, where we may think about removing the operator out of the decision-making process when it comes to process optimization, then simulation is essential for that, as an essential component for that. And we have other things that we might want to consider in the future and with simulation. And if you think about being able to run simulation faster than real time, you can then get into this scenario where you can imagine an operator wanting to do a what-if scenario. And an operator might be sitting there and they may know from digital applications that they're slightly off the golden batch or slightly off the parameters that will give them the ultimate product quality. And they're thinking about making a change to a production set point. If they can make that change in a simulated environment and be able to run that 10 times faster than real time, so they can see if that change will actually take them to the destination that they want to get to. The value is huge. So we're even looking now at simulation, running it faster than real time, and giving our operators the chance to do what-if scenarios with the simulation, so that they can make much better decisions when it comes to making changes in order to improve their production or their production quality.
Excellent. Wow. Really good stuff there, Steve. I appreciate your time today. And I know I learned a lot, and I'm sure our audience did too. So thanks again for coming. And everyone out there, we'll see you next time or talk to you next time soon on Adapt Now from ABB Adaptive. Thanks.
Thank you. It's been a pleasure.